I'm Sanjoy Banerjee, Distinguished Professor of Chemical Engineering and Director of the CUNY Energy Institute. The CUNY Energy Institute is an interdisciplinary, interdepartment effort which covers various energy technology developments, as I show you in the next slide. The mission of the Institute is to develop low-carbon technologies that would increase our energy self-sufficiency in the United States and reduce energy imports. We cover mainly three technology areas. The first is nuclear reactors, nuclear energy, which has, as you know, a very low carbon footprint. And we have programs related particularly to small and modular reactors and the safety of such reactors. The second area is renewables. We have a large and very active program with regard to batteries for energy storage, which is very well funded from a variety of sources such as NASA, DOE, and so on. And then finally, we have a program in the oil, gas, water area, which is primarily focused on trying to minimize the impacts of oil gas production on the environment and to be able to do this in a sustainable way. There are many faculty involved in these efforts. Part of them are from chemical engineering, some from chemistry, some from mechanical engineering, and also from physics and so on. And as I'll show you, there will be a number of research associates and PhD students who work on the program as well. I'm going to focus primarily on my own work. There'll be other faculty members that you'll meet who, like Rob Messenger and Alex Kouzis and Elizabeth, who also work on the Energy Institute type problems. And we tend to use the Energy Institute as a way to bring people together, to support them, and to be able to go out for large grants such as multi-investigator grants from organizations such as the National Science Foundation, NASA, DOE, and so on. I'm going to show you a few accomplishments of the research program and then talk a little bit about where people go and so on. And this is primarily going to be related to my own work. So some of the areas I'll cover are related to high temperature gas-cooled reactors, a phenomena called relaminarization, which tends to reduce cooling if there is an accident. And then I'll talk a little bit about some advances we've made with batteries, as well as how we can control coalescence and emulsion breakup, separation problems in oil-water emulsions as we go on. So just three examples to give you a flavor of what's going on. So in the next slide, I give you some examples of these projects. In the renewable energy area, we've decided to focus primarily on energy storage. We don't work so much on photovoltaics or things like that, but basically, as you know, these solar and wind type resources are intermittent, and therefore they need to be stored in periods where there's excess production compared to use, and then used, for example, at night when there's no production from solar, for example. So energy storage has become really a vital part of going renewable with our energy economy. And some of the real advantages of doing this is that you can put things like batteries relatively close to where the energy is being used. So the energy may be produced, in areas which are relatively remote from where they're being used, for example, in cities where there's a lot of uh, usage of energy, but the generation of solar and wind energy may be from areas outside the city, but the batteries can be located close to, say, buildings or within buildings and so on. So some of the areas we've been working on at the Institute are the use of zinc in particular and aluminum as well as energy storage media. So we have zinc anode batteries, aluminum anode batteries, and we've been studying things like electrodeposition, dendrite control, and the cyclability of anodes made of these very high capacity, relatively inexpensive materials. So the excitement recently is a technology here which is beyond lithium, much lower in cost, and which can be used for massive grid storage as we go forward. So one of the other areas that we are involved with is in, as we call it, the oil, water, gas nexus. You know, production of oil and gas is very important to the nation. In fact, the advent of fracking has made us largely independent of foreign oil gas reserves, which is very important from a national security point of view. However, these types of technologies bring with them environmental effects, and one of the effects, of course, is that the produced water tends to contain contaminants, as well as it's difficult to handle. It can go back into the groundwater. So there are many environmental type issues, and even separating out the oil from the water is sometimes quite difficult to clean up the water because vestiges of oil tend to stay with the water. So there's been quite a large program that we've had funded by the National Science Foundation to look into the fundamentals of these phenomena. For example, you know, what stabilizes oil-water emulsions, how they might be broken, and how they can be separated. And there are lots of very important fundamental problems that have to be tackled to make these processes easier. And finally, we have a very substantial program on nuclear energy. This is supported by the Department of Energy. We are looking at very high temperature gas-cooled reactors, and particularly their safety. These are small modular reactors which can be deployed fairly readily, and they have many advantages. If there's any accident or something, they can be easily air-cooled by natural convection. And some of the issues that arise there is, you know, the heat transfer that occurs between, say, air that comes into the system in an accident condition and the cooling effect of the air when it's exposed to very hot walls. And so there are lots of interesting fundamental issues that arise there. So to move on, here I show you what happens at the oil-water interface that we've been studying. In particular, the adsorption of certain constituents of the oil, which are called asphaltenes. These heavy fractions tend to go to the interface of a drop, for example, of water in the oil, and they form a sort of a film on it, and they block coalescence, so that in the oil-water emulsion, what you tend to get is almost like a skin being formed. And if you look at the picture below, that's a water drop being contracted, and you can see that the surface of the drop develops wrinkles on it as if there's a skin, you know, and this is really a constituent of oil which has adsorbed on it and prevents the water droplets from coalescing. So it's very hard to break oil-water emulsions and clean the water of oil droplets eventually, because the interface is very stable. and there are demulsifiers which are used to make this happen. So this is a typical example of a problem that we are interested in. We're also interested in how, these asphaltenes may adsorb onto rock surfaces and change the wettability, which gives rise to effects that don't allow you to extract as much oil from a formation as you would if the rock could be wet with water, which would allow the oil to be driven out. Whereas when you have these asphaltenes adsorbed on the surface, what tends to happen is the surface tends to become oil wettable, and much of the oil gets retained then in the formation. In the next slide, I show you the problem related to the nuclear reactor problem. Here you see that you've got, let's say, a hot gas, which is flowing through a very, very hot wall tube. And as you go up the tube, the wall being very hot tends to increase the viscosity. Viscosity increases with temperature in a gas. And therefore, what tends to happen is when the flow comes in, it could be high enough in velocity that it's turbulent. As you can see, the velocity profile towards the entrance, which is shown in the left bottom slide there, or panel, is quite flat, which is characteristic of a turbulent flow. But as it goes up the pipe or tube, what you see is the hot wall tends to increase the viscosity and laminarizes the turbulence. So you get a typically parabolic profile in the velocity, which gives rise to a deterioration in heat transfer. So the wall temperature actually goes up significantly, as shown in the top panel on the left-hand side, as you go up the tube. And this is very important because it reduces the heat transfer and cooling of the air or gas that's coming in that would be used to remove the heat from these high temperature reactors in case of an accident. So we are one of the centers here which is very, very active in trying to understand how this happens and how to improve the heat transfer. Next slide, I show you some work we've been doing with regard to zinc manganese dioxide batteries. This work has been very successful. It's led to a spin-off of a company. We've been awarded the Green Chemistry Challenge Award for this work, as well as most recently the company that was spun off won the New Electrochemical Technology Award from the Electrochemical Society. So EPA, DOE, ACS, there'll be many recognitions of this work now. Basically, several breakthroughs were made. One is the ability to use the full capacity of manganese dioxide in a zinc manganese dioxide battery. A zinc manganese dioxide battery you're very familiar with. It's the usual AA, AAA cells that one uses. However, in this case, what we've been able to do is to make it rechargeable. And not only rechargeable using some part of the capacity of the manganese dioxide, but by using dopants to be able to make it rechargeable so the whole theoretical capacity of the manganese dioxide can be extracted. And this is illustrated, in the slides on the left, where you can see that by adding dopants such as bismuth and copper, we've been able to stabilize the crystal structure so that it comes back repeatedly in identical form as energy and capacity is extracted from the battery and put back into the battery. So this has been a major breakthrough. Another major breakthrough has been the use of dual electrolytes, where on the zinc side we've used an alkaline electrolyte, and on the manganese dioxide side, we've used an acidic electrolyte. By doing this, we've been able to get the voltage of the battery to almost 3 volts. Typically, in an alkaline zinc manganese dioxide battery of the type that, the primary cells we are talking about from Duracell or Energizer, those voltages are about 1.4 volts, but this is almost double that because we're using a dual electrolyte. And this has been another major breakthrough, and it looks like we now have an alternative to lithium-ion batteries, which have a higher voltage, typically around 4 volts. But of course, the cost of the lithium-ion batteries is much higher, and we are able to make batteries for a fraction of the cost. So this is a major breakthrough, and so this part of the program is extremely well funded. We've got very strong support from the national laboratories as well as the Department of Energy, plus investors who are interested in making this into a commercial proposition. Just to show you where the students go in the next slide, I'm going to show you the PhD students that have graduated from the Energy Institute since its founding, at least in my group of the Energy Institute, since its founding in 2008 when I came here from the University of California, Santa Barbara. Many of these students, of course, we've worked closely in collaboration with other faculty members, because one of the whole ideas behind the Energy Institute is to engender collaborations. So many of these students have been supervised in collaboration with Alex Kouzis, that you will meet, as well as Rob Messenger, and so on. So you'll see that most of the students who finished their PhDs here, and about 8 or 9 of them have finished under my supervision, have gone on to work in various industrial enterprises, for example, Intel, Corning, and so on. So this is very typical, Air Liquide, and so on. And this, you can get an idea of where they go. These are the current PhD students I have. Most of them here are working on energy storage. Shahaye, though, is working on oil-gas interface problems, and she's been doing a lot of simulations using lattice gas methods, and also most recently molecular dynamics. We work together with Professor Koplik here, who is also in the Levitch Institute, and he's in physics. The other students, Snehal and Michael, are almost finished, should be graduating very soon. They've been working on zinc manganese dioxide batteries, and most of the other students, Brendan, Jung Song, and Deban, are also working on zinc manganese dioxide batteries, various aspects related to the detailed structure of the processes that go on. We do have substantial funding in all these areas, so we are able to accommodate many new students as the work is very well funded. And here I show you the postdocs and research associates that have been in my group and where they've gone. Many of the postdocs and research associates who come on are really here to go beyond their PhDs and prepare themselves for academic life. And you'll see that the vast majority of them have gone on to academic positions. So at the University of Colorado, University of Leeds, Nagoya, and all over the world, actually. So that gives you an idea of the research group, the types of problems we are tackling, and I hope very much that you'll consider us for your graduate work. And I'll be available also on Sunday when we'll have a sort of an open house to answer any questions. So thank you very much.